Okay, this is my attempt to do like a quick version of the Quadratics lesson that we have been reviewing that we did on Thursday and Friday, which is October the 8th and 9th. Anyway, I'm probably going to chop this down anyway. All right, let's go through let's do a quick review. All right, so we started out in the warm-up and we want to do the transformation of this graph. Okay, so we did f of x, all right, equals x, and I believe that was x cubed. We got that graph right here. Then what if we change that to g of x equals to x plus 2, and I want to cube that, and plus 1. Okay, now look at what happened to the graph. Put a projector mode here. See, all that really happened here is the graph. If you look at that point and you look right here, you can see that, not that one, but you see this point, you just moved over 2 to the left and up 1 to get to that same area. So that lets you know that the correct answer to this problem is C. So I'm just going to just add an item. So the correct choice is C. All right, because all we did was the plus 2 means that we moved to the left 2 units, and the plus 1 outside of parentheses means there's a vertical shift up. All right, so let's quickly go to the next warm-up problem. Okay, this is just more the same thing. Then the next thing we did was we did an actual transformation. All right, so I want to take a graph. Let's see, matter of fact, let me just do another blank one. All right, and with this term we got f of x squared. Well, f of x equals to the square root. See, I type that x. And what we want to do is create a new function called g of x. Oops, that's typed wrong. G of x, and I keep typing the wrong thing. All right, and what we want to do is take this same f of x, which I'm going to show you how I got the square root symbol. I just put down here and got it, x. We're going to take that same g of x, but this time we want to reflect it across the x-axis, which means that we want to negate it. All right, multiply by -1. That's a reflection. Now, but since we're still in the a value, we want to also stretch it by 1.5. So, or 1 5/10. Now you see how the graph is stretched there? And then now we want to come outside and raise the graph up 1. And that's where you get the graph. If I can cut off the original function, you'll get the transform function there. So there's the original, that's the transform function. All right, so and so that's how we got started. Now we went to some applied problems here. Let's see, this is one. All right, this time we wanted to, and I just want to go with another blank. I want to save this. All right, let's go and let's go. All right. So now the height of a golf ball in the air can be modeled by the equation, and I'm going to type it. H equals to a -16 t squared, right? Plus 76t. All right, that's the height of a golf ball. We want to figure out 3 things: how long the ball was in the air, what was the ball's maximum height, and when will the ball reach its maximum height. So let's see if we can play with the window here so that we can kind of see what's going on here. So what I'm going to do is, let's see if I can move this over just a little bit. See if I can get a little more screen real estate here. It might be all maxed out here. See, is that all you can go? No, I'll just move this over where you can see what I'm doing in Desmos. All right, just look to the left. I'm clicking on my little graph settings icon right there. And as you can see, I'm in projector mode because I just love projector mode. All right, what I want to do is I want to change my graph so I can see it better. So I'm going to look at my X. Let me clear this out for me. Look at this graph here. I can't see the top of it. So I'm just going to take a wild guess and I'm going to change my Y value. So I'm going to go up here to my Y axis. See, it stops at 14. I'm going to take that up to like 200. And I can tell you already that's almost too big, even though that does help us answer the question. Let me take it down a little bit. Let's take it down. Looks like I just need like 100 to get the job done. Right? So there, that's better. And what if I wanted, you see how I got this extra stuff here? I don't need all this extra stuff. I'm just gonna go from, I'm gonna let the x-axis go from -5 to +6. So I'm going right here, I'm taking my x-axis, I want to go from -5 to +6. Alright, when you do that, you get a much nicer graph there. So now we got a graph that we can take a good look at. So how long was the ball in the air? To figure that out, the x-axis here, and you can't really see it now, you can. And now I see how now I almost need to shrink this graph just a little bit more. But I think that you can kind of see what's going on. All right, I am going to shrink this just a little bit more. I'm going to take the y-axis down. I want that to go to like 150. Yeah, now that's a lot better. Now you can see everything. Okay, so let's get back to it. So if I want to figure out how long the ball in the air, I look at the timeline. See, the ball, h is the height in feet of the ball after t seconds. Okay, so this is the timeline. That's t. So if I click right here, if I can just get this thing to click right there. Oh, you know what? It's trying to move me around. Now let's do it. There we go. All right. So if I click right here, notice the x-axis is the timeline. So that's telling me that the ball is back on the ground in 4.75 seconds. It is. All right. And look at this point that's already highlighted. This tells me the maximum point on the graph is the maximum. So it tells me the maximum height is 90, just over 90 feet, and that it took, the x values is the time, so it took only 2.375 seconds to get there. So I got all that just from graphing the function and getting the maximum in one of the zeros. Okay, so let's go to the next slide. We do this. Okay, all right, I'm just moving on. All right, now here's the same, this is the same information that I just found out with Desmos. Now, what if I want to know when will the ball be 50 feet in the air? This is when I need to graph something else. I need to graph h of t, time, and I want to know when is the height going to be 50. And Desmos is going to put a vertical line right there that crosses the graph 2 times. So this tells me that the height of the ball is 50 at 70, about 0.79, and the height of the ball is 50 at about almost 4 seconds. All right, so 0.79 hundredths of a second, or 79 hundredths of a second, or almost 4 seconds. The ball will be 50 feet up. Okay, so we got another example like that. All right, so let's keep on moving. Let's keep moving. All right, so let's get some more examples here. See, I'm going to go ahead and clear this out the way. Don't want to save it. All right, so let's blank. All right, because I want to be done in about 5 minutes. So let's look at this. A dynamite blast and a quarry propelled a walk in the air. The height and feet of the rock above the ground is given by S of t equals 110 t minus 16t squared. All right, we want to know what in seconds, and time is greater than 0. So we're only going to look on the axis greater than 0, which is fine. We don't care about that stuff anyway. It says, at what time would a rock be 150 feet above the ground? So this is where I'm going to when would a rock be 150 feet up? Now I can't see it. You know why? Because I can only go up to 10 feet in this graph. So this is where you can either do a zoom out. Now the graph is getting really skinny and hard to read. I don't like that. So I'm going to go back and put in the axes I want. I'm going to let my x-axis be between, let's see, -3, and I don't need it to be that big. It looks like it comes down about at 5, so yeah, that's good. And then I'm going to let my y-axis, I need to get up past 150 feet. So I'm going to let y go from 5 to 200. All right. Now if I do that, now I got a really nice graph, and I can see that the 150 line, which is blue, crosses the graph here and there. So that lets me know that in 1.875 seconds the graph is at 150. Also in 5 seconds the graph is at, the ball is at 150, which lets me know the answer is C. Alright, so let's go on to the next problem here. Alright, so the answer is C there. And I don't know, I went fast, and I also have a red there. Now let's look at number 21. I like this problem. Let's try, let's get a blank one. The height and feet of an object projected upward as a function of the elapsed time in seconds since it was launched can be represented by the formula shown below. What formula? This one. H or T equals, I'm just reading the problem, 16t squared, alright, plus V, yeah, we'll explain that in a minute. I'm just typing the formula, plus H. Okay, alright, so those are my variables. I'll go ahead and let Desmo create some sliders, because that's what he's going to do when you have a variable that it doesn't know anything about. But here we've got some help. In the formula, H of T is the height in feet, so that's what we're calculating. T is the time in seconds. V0 is the initial velocity, and H0 is the initial height. So an object is projected upward with an initial velocity of 50 feet. Remember, VO is the initial velocity, so I'm going to make that 50. All right, and then it says from a starting height of 9 feet. So the initial height is 9. So I'm going to make, and if I can just move me out the way, I can make this 9. All right, so now I got my graph. Now again, I'll play with the window to get it right. I don't need a whole lot. I'm just going to drag this around. I'm going to make that, I can just drag it. And let me just make the graph a little, I'm going to make this y-axis a little taller. See what happens if I take that up to 100. That's too big. 50 to get the job done. I need a little on the top. Go at 70. Yeah, that's good. And I can get by. I don't need all this extra space at the bottom. So I'm just going to take my x from -1 to 5. That's what I'm going to do. Take my x-axis from -1. See, I'm just building my window around the graph, so that way I get a nice picture. All right, see how I use that? So now what are we trying to find here? We want to find when the object will hit the ground, which tells me I didn't need to do all this stuff. All I need is just when it hits the ground right there. 3.29. So that's approximately 3.3 seconds. So the answer here is A. All right. So let's keep on moving. Right. So you got to listen to this slide. All right. How you doing? All right. Yeah, I'm almost out of here. Okay. All right. So we're in a home stretch here. So a car collides with a truck that suddenly broke down the highway. And I'm going to go ahead and clear this graph out the way. All right. And a police officer investigating the skid marks made by the car after the brakes were applied measures the length of the skid marks of the car to be 225 feet. The officer determines that the speed of the car using the formula is S equals the square root, SQRT, I just typed that, 21D. All right, those are the immediate graphic. All right, well, S is the speed of the car and miles per hour when it begins to skid, and D is the length of the skid marks measured in feet. So what is the speed of the car when the brakes are applied? I know it's misspelled. Round the answer to the nearest 10. So we know that the skid marks is 225 feet. That is D. D is the length of the skid marks measured in feet. So what if we let D be equal to 225? If we do that, then we see that S is 68.73. So the correct answer to the nearest 10 is actually going to be 68.7. So 68.7 is your answer to the nearest 10. So let's keep moving. All right. So and now let's see, a soccer player kicks a ball at an angle. The height of the ball in feet varies with time and is given by the function h, t. I keep hitting the wrong notes. There we go. H of t equals to a negative 16t squared plus 33t. Okay. Remember, t stands for time. All right. And we want to know, well, t is the time in seconds. So what is the maximum height of the soccer ball to the nearest feet? So this equation, this graph gives the height. We just need to find a maximum height. In other words, that right there. So I don't necessarily have to make the graph pretty, but you know me, I just want to. I'm going to let my x-axis go from -2 to about -4, just so I can give me a nice pretty graph. So I'll go right here. I'm going to take my x-axis from -2. Believe me, you want to get good at this. -2. Did I say -4? I meant +4. That's what I meant. See how that's a nice graph, real easy to read. Okay. All we're interested is the maximum. So there's the maximum right there. And we see the maximum is the maximum height of the soccer ball to the nearest foot is just 17. So that's what you should put as the answer here, 17. All right, so the answer there is 17. And let's go on to the next problem. We're just knocking them out. I only got 2 more, so let's knock them out. All right, so here, blank graph. All right, I think you now see what the pattern is. Just to type the equation, the Texas Department of Public Safety collected data on the stopping distances for a number of different types of cars. It found that one brand stopping distance could be modeled by the equation y equals to 0.05, which is 500ths x squared. All right, plus 10 hundredths. So I'm going to go 0.10x, 10 hundredths x plus 5 and 0 tenths. All right, so here's our graph. They found that one brand stopping distance could be modeled by the equation I just typed, where y is the stopping distance in feet and x is the speed of the car in miles per hour. So if a car required 100 feet to stop, what was its approximate speed before beginning to brake? Okay, so this equation models the stopping distance. We want to know if it y is the stopping distance. So this is the y-axis is the stopping distance. So what happens when y is equal to 100? So let's just go ahead. When the stopping distance is 100, we want to see what happens. What is the speed? That would be x. So let's take this graph up a little bit. I think I can get away with just zooming this one the other way. Yes, I don't have to do anything but just zoom this one. And we're looking at what is the speed when the stopping distance is 100. 42.6, which is choice A. Okay, last question. I think, no, we got two more. Is there two? No, that's the last question. Here comes the last question. All right, so clear it out. And let's see. All right, here it is. Height of a toy rocket launched from a 64-foot observation tower as a function of elapsed time since the launch is modeled by the equation h t equals -16 t squared plus 48t plus 64. Okay. All right, so there it is. So what we want to know is at what approximate lap times will the toy rocket be at 90 feet? So when is the height, when is h of t, which is the height, when is that 90 feet? Can we see it? Of course not. So we need a zoom. Okay, we can zoom out, but I know this graph's gonna get really skinny. I'm gonna do it anyway. Oops, I always go the wrong way. All right, yeah, look at it, real skinny. All right, all I need is just let's go between 5 and -5. I'm just gonna change my graph settings to X. All right. If you want to really get good at making these graphs look great, send me a chat or something so that maybe we can get you in my intervention class. All right, see that? Nice graph. Okay, actually we kind of overdid it, but that's good. So let's see what we got here. We want to know at 90 feet, that's the blue line, what we got going on here. At 90 feet, we see that the rocket will be at 90 feet in 0.7 tenths of a second and at 2.3 or 2.29 seconds, which is choice J. And that completes our little mini class on Desmos and solving equations. And this is a 20-minute video, all right, which I'm gonna cut it down. All right, have a wonderful weekend.